me just for repetition go over it. Give you a little detail about what to expect for the test. The best way to see what to expect for the test is to look at the old exams, but with the knowledge that it's not going to be the same questions. You might see a few of the questions repeated, but I rarely repeat questions, so I'll write new questions for you. But they'll be similar. Also look at the homework, the supplemental problems we're working, um, the notes, the concept tests. Those concept tests I'll often pull multiple choice questions. So you'll have 15-ish multiple choice questions and then 4 to 6 free response questions. Those multiple choice questions will largely be just conceptual, so no calculations. You might have some very simple calculations, but largely just conceptual. And then the free response will be, you know, word problems. You'll have a graph, you'll have a function that you'll need to take the derivative and or integral of in order to find the velocity, displacement, or acceleration of an object. You'll also have a graph that I'll write this down, but you'll have a graph that you'll need to qualitatively describe and quantitatively describe. Like we've done that where you calculate the slope from the graph or you calculate the area from the graph, that sort of thing. And if you look back at the old exams, you'll see questions that are similar to that. Okay, let me write this down. So we have from chapter 1, dimensional analysis. That's where I give you equations. You tell me are they correct or not. Might have some basic trig where I just give you a triangle, or I give you coordinates on a coordinate system and I ask you what is the distance or the angle. We did that in class. Estimates, where I give you some common item and I ask you the volume, area, length, or mass of that item in meters, centimeters, or kilograms, or meters squared or centimeters squared. Sig figs, where I give you a mathematical operation and ask you to either give me the number of sig figs in the answer or the right answer with appropriate sig figs. Standards and unit conversions. The standards for length, mass, and time. Be careful because, you know, we did talk about how those standards have changed over time, like for the meter or for the kilogram or for the second. And you'll see the old standards sort of peppered in with the correct answer. So just be careful that you know what the current standard is, but also be familiar with what the old standards is, just so you don't get confused. And then unit conversions, converting, say, meters to centimeters, converting meters per second to kilometers per hour, or something similar, and converting something like centimeters cubed per second to meters cubed per second. So when you have a cube or you have a square in the unit, so you have to square or cube the unit conversion factor. These are probably all going to be multiple choice for the most part. With the exception of the dimensional analysis, you might have a free response question for the dimensional analysis. Okay? So chapter 1 will largely be in the multiple choice except for the dimensional analysis. I probably will put a dimensional analysis question in the free response. From chapter 2, we have that derivation. I'm just asking you to memorize it. If you just memorize the definitions of acceleration or velocity and acceleration, and if you know how to do integrals, and if you know how to do integrals, then the derivation is simple. If you just want to memorize the steps, that's fine too. But it'll be a free response question, or it might be a free response question where I just ask you to derive the equations of kinematics, and you have blank space, and you'll put in the derivation. All right, did that in class. I'm just asking for what I did in class. Um, you'll have some graphing problems, and I'll write qualitative here. That's a qualitative, Q-U-A-L. That means that you qualitatively describe the graph. So this graph of position versus time is showing an object with increasing positive velocity or with negative acceleration. We did several of those in class. Look back at the old test, you'll see some like that as well. I might also give you a scenario and ask you to draw the position or velocity versus time graph. Kind of like we did in that lab. I know not all of you are in lab, but in the lab where we did the bounce pass, the pass, and the drop. Or like we did in class, we had some questions like that in the concept test where you had to pick out the graph that was describing a certain physical scenario. Okay, So graphs qualitative, graphs quantitative. That's where I give you a graph and you either find the slope of it to describe, say, the velocity or the acceleration, or you find the area under that graph to find the velocity or acceleration. Often what I do with this is I give you a function that describes this graph, and I also give you the graph, and I have you find the answer in two different ways. By calculus, where you either do the derivative or the integral, follow what I'm saying, and by just doing it by drawing it by hand. And then you can check your answer, because they should be very similar. Look back at the old test. We did some in class too, but look back at the old test and you'll see problems like this. You will see a problem like this. You will see, we see all these. You may or may not see the derivative. I don't know. That's a surprise. Okay. I don't know yet either. So graph, qualitative, quantitative, and then also you'll have some kinematic word problems. Kinematics, word problems. Let's see, you'll probably have a couple of these. They'll be like ones that we've worked, like ones in the homework, like these supplemental problems. Um, they might be a little simpler than these supplemental problems, but you'll still be exercising the same steps in them. I'll try to make them, try to strip away all the extraneous steps, unit conversions, all that little things, to sort of the bare meat of the problem, bare bones of the problem. Okay, dokie. How y'all feel about this exam? Feeling good? It, I know, but it'll probably be the easiest exam of all semester, so we want to do well on this exam, okay? Because, you know, the material builds on itself as we go along, and so you want to do well on this exam. You want to make sure that you've mastered this material before we move on to the next bit. I'm around the next couple of days. I'll be around for my office hours. I'll try to be around all the time. So if you have questions, feel free to drop in. Um, all right? Okay. You all look very excited about the exam. Yeah, Nicole? Oh, I'm sorry, Nicole, and then Asia. She raised her hand too. Right. You're not gonna. So back in chapter 1, we did derivatives and integrals. You're not gonna see that except for in the context of these things. All right. Let me go back and show you a problem. Okay. I'm not gonna work about it. We've already worked it in class. And then Asia, what's your question? No, you don't need a Scantron. I'll give you a sheet that has the bubbles on it for the multiple choice part, and then you can bubble that in. All right. Um, like this problem, this is problem number 5 in the homework. This is what I mean. You will have a problem like this. I haven't written it yet, but I'm certain that you'll have it. I give you a function for either x or v. I tell you to graphically determine the position's instantaneous velocity. So I give you the graph of that function, and you graphically determine various things, the velocity, the acceleration, the distance traveled. All right, by drawing a line, by shading in the area and calculating it just from the graph. Um, and then I also, and then you also have to find the acceleration with calculus, either through an integral or a derivative. So you will have to do integrals and derivatives in the test, but not all by themselves like in chapter 1. So you won't have to do integrals or derivatives of trig functions, and you won't have to use the chain rule. You will not use the chain rule. We're going to use that later in the semester. I just sort of threw it in just to, I don't know, because, you know, it's the chain rule. Does that answer your question? And we answered yours too, right? Yeah. Any other questions about the test? Okay, I think that y'all are probably ready for it. You know, get good sleep tomorrow night. You'll probably have other tests this week too, am I right? Yeah. Okay. Sure. Let me show you what I would expect to see. So you have two kinematics equations. You have V equals V naught plus AT. That's the first one you would derive. And then you have this one, X equals X naught plus v naught t plus 1/2 at squared. I would expect to see, first of all, that a is equal to dv dt. To start with that, that's our definition of acceleration. Then we would say dv equals a dt. All I do is I cross multiplied there. dv equals a dt. I integrate, and I get v, the integral of a dt is at, plus my integration constant, which is v naught. Right, that would be the first one. And then the second one would begin with not a, but v equals dx dt. Dx equals v dt. Integrate both sides. X equals the integral. And now this is where it starts to get a little bit different. I put this in for v, at plus v naught dt. When I take that integral, I get 1/2 at squared plus v naught t plus the integration constant, which is x naught. I would expect to see all those steps. If I didn't see one of those steps, I'd count off. This will probably be worth, if it's on the test, it'll be worth about 10 points. Okay? So if you missed a step, I'd count off, a couple points. Or if you just didn't do this whole part, I'd count off 5 points. All right? Remember what I said about the test on the free response. It's better for you if you can clearly show me all the steps that you take, because if you just write an answer down and it's wrong, I count off all the credit. If you don't have any steps or whatever, in fact, if you just write down an answer and it's right, I don't know. I've never had that happen, but I would raise my eyebrow at that, and probably we'd talk about it. But just clearly mark all of your steps, and it'll. If you get something right, you'll get something out of the problem. I'm generally fairly, what's the word, generous for partial credit. Okay. All right. Let's work some of these supplemental problems. Did that answer your question, Nicole? Yeah. Not guaranteeing that it's on there. The graphing thing will be on there. The derivation, sort of. We'll see how the other problems. I don't want to make it too long. Oh, and then the class, we will meet at 7:15. It's not required for you to come at 7:15 on Wednesday, but I give you that extra 15 minutes, and then we go until 8:30. So you get an extra 5 minutes at the end. So you really get an hour and 20 for the class, and then it gives you 5 minutes to get to your next class. Okay. Let me know if that's a problem. All right. Let's look at these other supplemental problems. This one's kind of long, and like if you saw something like it on the test, it would probably be stripped down. It wouldn't have as many parts, but it's a fine problem otherwise. It says a bicycle racer has a velocity of 11.5 meters per second. At the end of the race, he accelerates at a rate of 0.5 meters per second squared for 7 seconds. So what he does is he's riding along. I always like to draw a picture. A bicyclist, you get the idea. He's riding along at 11.5 meters per second. He's going along. And then at this point, he begins to accelerate at 0.5 meters per second squared for 7 seconds. All right. So at some point during the race, towards the end, he begins to accelerate. And the first question just is, what is his final velocity? Whenever I'm working these kinematics problems, and I recommend that you do the same, I just write down my kinematics equations. V equals V naught plus AT, and then X or Y, as it may be relevant, equals V naught T plus 1/2 AT squared. Notice I left off the X naught. The first one just asks, what is his final velocity? Well, I want to know what is his velocity over here. Right, you get the idea. What is the velocity over here? I know his initial velocity. His initial velocity is this amount. So I'm going to write all that down. V naught equals 11.5. I know that he accelerates at a half a meter per second squared. And I know that he does that for a time equal to 7 seconds. See, all these are 3 sig figs. Okay? And now I want to know what is his final velocity. I look back at my equations and I say, well, this is the one that I want to use because I'm looking for this and I know everything else in that. So I can solve for that final velocity. It's 11.5 plus a times t, 0.5 times 7, which is going to give me 15 meters per second. So that's his final velocity. Now in part B, it says that a race continues at this velocity to the finish line. If he is 300 meters from the finish line when he started to accelerate, how much time did he save as compared to if he didn't accelerate at all? Yeah, Catherine? No, no. Let me take that back. If you're wildly off, yeah, like if you give 7 sig figs and it should be 3, then I'll probably notice. But if you just give 2 sig figs, like I used the wrong sig figs too that night. It should be 15.0. But if you give 2 and it should be 3, I'm not gonna notice. I'm not gonna count off. Okay? Does that answer your question? So don't put 6 where there should be 3. So, all right. And if I did count off, it just 1 point or something. If you did put 6 instead of 3. Okay. Where was I? Oh, so we need to calculate 2 times for the second part. I want to calculate as if he didn't accelerate at all, and then the time required when he did accelerate. So we're looking just for this last 300 meters. So the first part, B, we'll say, what if he didn't accelerate? What's it going to be? Well, V will be 11.5. X is 300 meters. And so T is X over V. That's just going to be 300 over 11.5. Which is 26.1 seconds. I know that we haven't really seen this, but this is really just a simplification of one of our kinematics equations. It was the x equals v naught t plus 1/2 at squared. We're letting a equals 0, so that whole thing goes away. So it's really just this equation, but solving it for t. And since v isn't changing, I just changed the v naught to v, because v and v naught are the same. All right. Useful to look at the units too. When we're thinking about simple kinematics problems like this is meters over meters per second. That gives us seconds. All right. So that's the time without acceleration. With acceleration, we want to know what time it takes. We want to find out a couple of things. What distance does he travel while accelerating? All right, so I'd say x equals v naught t plus 1/2 at squared. So he starts accelerating. What is his velocity at that time when he starts accelerating? The 11.5. That's when he's traveling that velocity when he starts to accelerate. And then he accelerates for how long? 7 seconds. Right, these are all in the problem. We know his acceleration. It's, what was it? 0.5, and then t is 7 seconds again. So we can calculate that distance. It's going to be 11.5 times 7 plus 1/2 of 0.5 times 7 squared. And that's equal to 92.8 meters. Right, it said he was 300 meters from the finish line. So after he accelerates, he has 300 meters minus 92.8. That's what, 207.2? He has 207.2 meters left. And so now we want to know how long does it take him to travel that distance. So how long to travel this? That's going to be, he's traveling now at a new speed of this 15 meters per second because he's accelerated at this point. He has 207 meters to travel, and the time is going to be x over v. That's going to be 207.2. That's the distance left to travel divided by 15. I get 13.8 meters per second, or excuse me, seconds rather. All right, so the total time, how do we find the total time that it took for him to travel this last part while he was accelerating? The total time? Well, we have two parts to it. It's 13.8 seconds. What's the other part to the time for him to travel that last 300 meters? 7 seconds is right. So 13.8, and then we have that extra 7, so it's 20.8 seconds. So total time is 20.8. And we've already found that it took him 26.1 seconds. So the difference is 26.1 seconds minus 20.8 seconds. And then that's equal to 5.3 seconds. So that would be the answer. This is without acceleration, and then this is with acceleration. A lot of these problems are just reading the problem and being able to pick out the appropriate information. That's not as easy as it sounds, especially if you're sort of new to this, but it can come with practice. There are kinematics problems in the old test. If you just work through all those and you feel like you need more practice, I want to point you to our website. There's a really good open source book. If you go to this OpenStax book it's on the website under online textbooks. Go to chapter 2. You can find all sorts of kinematics problems there. So if you just go to chapter 2, all about kinematics there. Everything that we've been doing is in chapter 2. So there are examples there if you want to see additional examples, and they're similar to what you'll see in this part of the test. Okay? They don't have any calculus problems, unfortunately, but if you need help with that, you can come see me. I can give you a textbook or help you with that on my own. Okay? All right. Let's do this last part. In the last part of the problem, it says, this one gets a little hairy. Another racer was 5 meters ahead of him when the winner started to accelerate. This other race was not able to, the other racer rather, was not able to accelerate and traveled at 11.8 meters per second to the finish line. How far ahead of him did the winner finish in both meters and seconds? All right, so we have two racers. I'm going to draw them as runners because runners are easier to draw. All right, this is the winner, and this is the loser. It says that he travels at 11.8 meters per second in this direction to the finish line. And we want to know how much time in distance and in time. So he has, we know this distance is 5 meters. So this distance to the finish line, we know to be 295 meters. Because we know that this guy is a total of 300 meters. So the loser needs to travel 295 meters to the finish line. So in order to find the time, equal to x over v. It's going to be 295 divided by 11.8. And that gives me 25 seconds. All right. But I know that the total time for the winner to run this is 20.8 seconds. And so to find the time that he was behind the winner, I just take the difference in those. So the delta t then is 25 minus 20.8, and that's equal to 4.2 seconds. And then if we also want to find the distance, we know we have 4.2 seconds. Distance difference, so it's going to be v, which is going to be 11.8. That's the speed of my loser, times 4.2 seconds, and that's equal to 49.6 meters. So he was almost 50 meters and 4 seconds behind the winner. You know, the application of the kinematics problems in this, or the equations, that's not real complicated. The complicated part is reading these problems and being able to pick out what the heck it's talking about. And you're probably looking at it now because, you know, it's sort of hard to watch somebody do this. You're probably looking at it saying, no idea what he's doing. Maybe some of you are getting it, but you should go back and read these more closely and take a look at them and maybe try them out on your own. Okay? All right, let's do this last one. Oh, this one's not as complicated. I'm sorry, I sort of worded this one not very well. But it says a player tosses a basketball straight up for the tip-off. At what velocity must a basketball player leave the ground to rise to 1.25 meters, 5 feet or so, above the floor in an attempt to get the ball, or about 4 feet, in order to get the ball? I have a player here. He needs to jump with a certain initial velocity, and I want to know what velocity that is so that he goes up to a distance of 1.25 meters. And then he's going to come back down. So what velocity must he jump in order to go up a distance of 1.25 meters? If he goes too slow of a velocity, he's not going to go high enough. If he goes too big of a velocity, he'll overshoot the 1.25 meters. I know a few things about this. I know the acceleration. What's the acceleration? Negative 10 meters per second squared. It's a free fall problem. It's vertical direction. So if you're in the vertical direction, just assume that it's going to be negative 10. I know a couple of other things. I know that the velocity here is equal to what? Right, the velocity at the top is equal to 0. I know the distance, y, is 1.25. And I think that's all I need. Is that right? I think that's all I know. Now I'm going to write my equations over here. I have y equals v naught t plus 1/2 a t squared. And then I also have v equals v naught plus a t. Now I want to look at those and ask myself, what are my knowns and what are my unknowns? Well, the thing that I'm looking for is this. I want to know that value. Yeah, Tyler? Oh, no, that was a mistake. Would you like for me to write it as acceleration? No, that would be wrong. Thank you, Tyler. All right. Do I have another unknown in this equation for v? I don't know t. So that's going to be a problem because I don't know t and I can't solve for v then. Now I look at this other equation. I know y. I don't know v naught and I don't know t. And I don't know t there. So I have two unknowns and I have two equations. you will have a system of equations. I'm almost certain. I'm 95% certain that you'll have a system of equations. And this is a system of equations. You have two equations, two unknowns. You can solve it, but it requires substitution of one equation into the other. You've done this before. You did it in high school. But it's an important skill, and it's something I want you to be quick at. And you'll see it this test. You'll probably see it next test, too. You will see it next test. Okay? So how are you going to solve this? Well, there are two ways that we could approach it. We could solve this equation over here for V naught, and then plug it in over here for V naught, because then you would have this equation would only have t as the unknown. Right? Or we could solve this one for t, and then plug it in over here for t here and here. I'm going to solve it for t, and I'll show you why when we get there. So first of all, I'm going to take this V naught out. Oh, wait, no, I can't do that. Not V naught. I'm going to solve this for t. T is going to be V minus V naught over A. I can simplify this a little bit. Which of these values is equal to 0? V is equal to 0. So I'm going to go ahead and take it out, because it makes my substitution a lot easier. Listen, often with substitution, there's a hard way and there's an easy way. And the trick is to figure out before you start what is the easy way. And if I look at this and I think about how I'm going to plug it in over here, that t is equal to negative v naught over a, notice that when I do this, it'll come over here for t squared, and it's going to, I'm going to get rid of one of my accelerations. So I'll drop a quadratic term on this side. And then I don't have to use the quadratic equation, which is kind of a pain in the butt. So I'm going to plug that in over here for t. So I get y equals v naught times negative v naught over a plus 1/2 a v naught squared over a squared. All right? And now I get negative v naught squared over a plus 1/2 a, or excuse me, half v naught squared over a, because I lose this a and I lose an a there. Okay? Notice that I have common terms here, v naught squared over a, and so this is equal to negative 1/2 v naught squared over a. I have negative 1 v naught squared over a, 1/2 v naught squared over a. Negative 1 plus a half is negative 1/2 v naught squared over a. This is equal to y. So I can solve this for v naught. V naught then is equal to square root of negative 2ay. So I mean, this is a kinematics equations, but it's specialized. I wouldn't try to memorize. There are any number of possible variations that you could have depending on your situation. And that is equal to 5 meters per second. All right, so she needs to jump at 5 meters per second in order to go 1¼ meters up high. All right. Do you think about that before you jump? No, you just do it, don't you? Because you can do it in your head is the thing. Like even a 4-year-old knows kinematics. You just know you go through the equations in your head, but you don't even think about them. Right. Okay. Those are good examples of the word problems. Again, the second one is a little long because it took me a long time to work through it. So I would strip it down and make the steps less cumbersome. But that type of problem is something that you'll see on the exam. Also, look at the homework. The solutions are online for the homework, but if you have questions, we can go over them. I could do that today if I gave it to you. I'd love to see all yeses and happies. Okay, you'll be okay. It's going to be okay, but it's going to take a little work between now and then if you're not prepared right now. Okay, any particular questions for the test? sort of use this as a review time, if you like. Mechanical. I said it was ridiculous. Okay. What's the Nicole? Let's see. Let me remember this problem. Um, yeah, it's a little ridiculous. It's kind of complicated, but you will see free fall stuff, kind of like the basketball problem. Um, this is one where you had to think about the different distances that the sound travels, right? Yeah, and the rock, right? Yeah, you wouldn't see one that complicated. You'll find that with the homework that it's, and even the supplemental problems, they might be a little more complicated, but they exhibit the same characteristics that you'll see of problems on the test. I'll try to simplify them as much as I can for the test. Does that help you a little bit? Okay. All right, what else, y'all? I'm not going to let you out early. I'm just, if you have questions, we can use this time for it. Otherwise, we can look at some other things. I'm not going to go to the next chapter, but we'll look at the old test and just sort of strum through it. We'll look at the one in the back of your book, then we can look at some others online. This is exam one. I just want to point out too, I did send out an email this weekend, but on the website, most of you know this, but on the website there is a link to old exams. Physics 201. You can use all these old exams. They're a good study guide for you. Mostly look at exam one. I think in a few cases, exam two might contain a little bit of it. Not that one. No, not that one. Not that one. Okay, maybe don't look at exam two at all. No, don't look at exam two at all. Okay, so just looking at exam one, back to 2010. Sometimes you'll see information on exam one though that we haven't covered yet, getting into vectors. If you see vectors, little arrows and things going in different angles, don't worry about that. All right, how about this exam? Does anything stand out to you or something that you want to work through? Got the multiple choice on page one. This is page 289. There's the dimensional analysis. Probably have a couple of those kind of like here. Sig figs, standards. Everybody feels comfortable with that? Okay. Yeah, Emma. This one? Okay. So how to find the acceleration? I'm sorry, can you repeat your question? Oh, the answer to A. Okay, yeah. So what are the values of x, of values 3 and 2? Well, x is equal to 3t squared minus 2t cubed. I know over here the units are meters, and so they have to be meters all the way throughout. So since t is second squared, then this has to be meters per second squared, right? It's just a dimensional analysis question. And then over here, since t is seconds cubed, what must 2 be units of, y'all? Right, meters per second cubed, seconds cubed. And so if you're looking at this function and you wanted to sort of guess, actually no, the acceleration is more complicated. Never mind. Okay, this is a good example of something that you would have, although likely, or no, not likely, you shall have a graph of this function as well, where I ask you questions about that as well. Okay? Y'all okay on these type questions? You know what to do if I give you a function? This is the x. If you want to find v, you take the derivative of it. So here, v is going to be dx dt. Is going to be 6t. I multiply this times this, and I reduce 2 by 1, minus uh, 6t squared. And then if I want to find the acceleration, it's the second derivative, or the first of x, the first derivative of v, dv dt. That's going to be 6 minus 12t. Okay? So yeah, that's what you have to do here and here. How long does it take for the object to return to its original position? Okay, on this one, since x is equal to 3, I'm going to rewrite it. I might have worked this differently on in the video, but 3 minus 2t. My original position is at x equals 0, and x equals 0 has two possible times that it occurs at. Do you know what those two times are? Right. So I have this equation there. If this part is 0 and if this part is 0, those are both possible options. So at t equals 0, x is equal to 0, and then at t equal 3/2 seconds. Yeah, t is equal to 3/2. X is also equal to 0. So it goes up and then it comes back down again. Was the velocity at t equal 0.5 seconds? In order to do that, you just plug in 0.5 here, and you can calculate t. And then at what time does it reach its maximum x position? Um, the maximum x position occurs when v is equal to 0. So you would say 6t minus 6t squared equals to 0. This is sort of like, it's not exactly the same, but it's sort of like something coming up and going back down, that the maximum x position occurs when v is equal to 0. And I would solve for this. I actually have two times at t equal 0, and then also at what's that, 6 seconds, I guess, at 1 second, and at t equal 1. And so t equal 1 is the right answer. You might have some little extra credit problems spread throughout the test, kind of like that. I'm not sure I haven't written it yet. Okay. Anything else from this test? There's a good kinematics problem. I would try working through that. It's similar to some of the others that we've been working. The words are all different, but the way that you approach these problems will be similar. Here's a graphing problem. This is what I was talking about, quantitative, where I give you a graph. You have to find the average acceleration between 1 and 3 seconds. 1 and 3 seconds. To find the average acceleration, you can think of taking the slope of that line. To find the instantaneous acceleration at t equal 2, you're taking the slope of the tangent line, something like that. And then to find the total distance between 1 and 3 seconds, we're finding the area under that function. That problem is going to be paired probably with where I give you a function. And so, as I said, you'll be comparing your calculus answers along with your estimates from just looking at the graph, your graphical way of finding the derivative or the integral. All right, might see a little trig. Y'all know how to do these. You'll see a couple of those. Yeah, Tyler. Yeah, I'll give you, like where I've asked you to find the area under the graph, for example, to find the distance traveled. Yeah, of course. Right. In fact, if you know what you're doing, as I said, I'll also give you the function. Here, I don't give you the function. but I'll give you the function so you can calculate the exact distance that it travels, and I'll ask you to do so, and then you can compare your answers and say, well, yes, this is really close, and they will be close, but they don't have to be exactly the same. All right. All right. You okay with these things? These graph problems? Um, does this graph have negative or positive acceleration? Negative or positive? This is a graph of position versus time. It's sloped downward in that way, decreasing. What is the acceleration? Is it negative or positive? All right, let's think. So a lot of people say negative. It has positive or negative velocity? Yes, negative because the slope is negative. The slope of a x versus t gives us the velocity. So the slope is negative and increasing. The slope is negative and increasing. And it's increasing. It's speeding up. And because of that, I have a negative acceleration, right? Because it's negative and increasing. Also be able to draw the v versus t graphs from the x versus t. You can see this, but my x versus t looks like this, and I want to know which of these represent the v versus t. Well, you want to look at the slope. Remember, the slope of this graph is represented by the value on this graph. Is the slope initially big or small, negative or positive? It's small and it's negative. So which of these start small and negative? Only one of them starts out small and negative, actually. Which one? A is the right answer. Small negative value, big negative value. Small negative slope, big negative slope. You'll see a couple like that, a couple of problems. They'll be in the multiple choice. Uh, or I might also ask you in one of the kinematics problems to draw the velocity or position versus time graph for that scenario, whatever the object is doing. All right. Okay, dimensional analysis. If you're not, that's okay. Any other questions? The format or particular problems you want to go over? Anybody? All right. Well, it is a little early, but I think I don't want to go on to vectors right now. But, okay. Good job to our football team this weekend. Lazarus, I'm sorry. It would have been awesome to win, but y'all did play a great game.